Okay. Now Edward will tell us about reference immutability.
Hi, my name is Edward. My name is Edward, and I'm going to talk about some joint work with my PhD advisor, Ondřej Lhoták, on reference immutability, hopefully simple, and System F sub. I apologize a little bit because I caught a bit of a cold this morning, so if I cough, sorry about that. So why am I here today? So pure functional programs are great because they're easy to reference, they're easy to reason about, and maybe this is a bit of a bad place to talk about this because this is OOPSLA, but don't worry, side effects are useful. Mutation is great. If we were to build a compiler, one phase you might write in your compiler is something like a semantic analysis phase, where you might want to collect a set of procedures in a map so that you can work with them later. And you probably want to build this symbol table of strings to procedures imperatively, because I'm not smart enough to do this pure functionally. I don't understand monad types really well. So mutation is often handy, but some mutation is bad. For example, in code generation, I've built my symbol table, but I probably don't really want to mutate it, right? Like if I accidentally modify my symbol table during code generation, that might be bad because it might introduce behavior I didn't expect. So what can I do to prevent this from happening? Well, one trick you might do is that you might say, well, all right, I'll make the symbol table private to the analysis phase. And when I need it in code generation, I'll expose a public getter method, like def symbol table, that'll fetch the table and create an immutable copy of it. So is that immutable? Well, I said it is, but I lied. This doesn't actually work. I can actually go and mutate. I can't mutate the table, but I can mutate the things that the table points to, the procedures, by reading through the table, asking for the procedure for main, and then modifying a field of it. And that's kind of bad. It's like, oops. And the problem is that while we created an immutable map, we created an immutable map mapping strings to mutable procedure objects. So that's kind of bad because we can still mutate values that were transitively reachable from the map, the symbol table. So to solve this, people discussed and introduced this notion of reference immutability. And what's reference immutability? Well, the idea behind reference immutability is that A, references can be marked read-only, and read-only references can only be read from naturally, hence the name read-only. But the one nice benefit of reference immutability, and the nice novel idea, is that references read from read-only references are themselves read-only. This viewpoint adapts references to ensure transitive immutability. So in this previous example, if I made symbol table return a reference, a mutable reference, then I can't modify locals because I read it through a reference immutable reference. So as a few examples, here's a few Scala-like examples, because this doesn't actually exist in Scala, but I know how to write Scala. Like, given a reference to a regular mutable reference to an object, I can mutate it. If I had a marker or a type qualifier for reference immutable references or read-only references, well, obviously I can't modify y here because it's marked read-only, but I can't modify y.first in this next example because, well, y is a read-only reference. Therefore, when I read y.first, I get a read-only reference to another pair. So there's a long line of work here, starting from about 2005. Java already did this for Java, and there was immutability generic Java and Ream for Java. Colin Gordon in the back worked on a really cool system for doing reference immutability in C#. And recently, I think in ECOOP, Vlastimil Dort and my advisor, Ondřej Lhoták, worked on a reference immutability scheme for Scala. And there's a long line of languages with reference immutability, D, Rust, for example. But formalizations have been challenging. So today, what are we going to do? I'm going to talk about some simple operational semantics for modeling transitively immutable references. And I'll hopefully give a simple polymorphic type system with subtyping, because we love subtyping, for modeling references given an immutable type. Now, how do you protect someone from tampering with an object? Well, if you're an Asian grocery store or my hotel, you wrap them up in saran wrap. You put lots of plastic up and you wrap your object up and you're like, hey, no one can modify that. And this is the sort of intuition we'll take here. We're going to start with the untyped lambda calculus with records, for the purposes of this talk and me, records are collections of mutable references. And we're going to add a new syntactic form, seal, which will wrap records, like saran wrap, but pass through other values. And when you get a sealed record, you can't write to it. And when you read from a sealed record, you return some sealed value, which may pass through or may remain sealed if it's a record or not. Seals capture this notion of viewpoint adaptation at runtime. The seal's viewpoint adapt references at runtime to ensure transitive immutability. And so, for example, if I have a record and my reduction semantics are over a pair of term and store, well, when I construct a record, I reduce the record to a record of labels mapping, something mapping labels to addresses, and where the value goes in the store. And well, like if it's an unsealed record, I can just modify it. So here, I construct a record with x equals 10. I put 10 in the store at location 1, and I set it to 5 so that, well, my semantics, I need to return something. So I return 10, but I update the store to have 5. So that's okay, but it also prevents bad things from happening, like seal of x at 10 dot x equals 5. I can't modify a sealed record. I set up my semantics so it gets stuck. And transitive sealing enforces transitive immutability. So when I have a record that's nested and I read a reference from it, I get back a sealed reference. So when I read from y, I get back a sealed x. And that guarantees transitive safety. So with this, we can show that the only way that seals affect reduction is in getting terms stuck. If you have two equivalent terms, one with no seals and one with more seals, then you can show with the setup that they'll actually reduce to equivalent terms, or one will get stuck, and there's nothing else that can happen. And if you want some math, because I love math, you can define how you would prove this is you would count the number of seals in a term, and you'd show that if you have two equivalent terms, or one has more seals than the other, then either they reduce the same way, or if the one with more seals will take a step and stay equivalent to the other term before it reduced, but you lose a seal. So, okay, nice lemmas. So seals don't affect reduction except in getting things stuck. Now let's talk about a type system so you can actually prove that you actually reduce. So types for sealed references, we're going to start with systemf sub for polymorphism and subtyping, because I like polymorphism, and really you want subtyping because immutable references are a supertype of mutable references. How do we model making references immutable, though, at the type level? So we have this notion of seals making term references immutable, so we'll kind of reflect that into the type system and add a type level operator read-only for turning a type into a read-only type as well, too. So there are some small technical details here which aren't really small and aren't really small or are really small depending on your perspective. It's kind of obvious that read-only string, read-only string, so on and so forth are all really equivalent types, right? But that's kind of hard to actually prove if you want to actually discharge this equivalence, especially in a formal theorem prover. So what we end up doing is we show that every type has a normal form with at most one top-level read-only that's equivalent to it. Since we model records with intersection types, this is actually kind of messy, so the details are in the paper. So with all that said, I can flash this slide, which is probably you see the slide all the time at a PL conference, which is progress and preservation. You can show that terms don't get stuck, and terms, when they reduce to the same thing, reduce to the same type. So that's good. This calculus I just talked about is sound, but what does that matter? Every reasonable calculus is sound. So what does this buy you? But this is where those equivalence lemmas I talked about actually come in really handy. Using progress and preservation, we already get for free that well-typed programs with sealed references to mutable records won't get stuck. And since writing to sealed forms gets you stuck, well-typed programs won't write to sealed references or references marked immutable at the term level. But there's a little catch here, which is how about references marked immutable only at the type level? References that are typed immutable, typed read-only, but aren't sealed. Can we say anything about them? But this is where those equivalence lemmas I talked about earlier come back. We have that programs that are equivalent modulo seals reduce in the same way, or the one with more seals will get stuck. So using those equivalence lemmas, references typed read-only can be transparently sealed without affecting typing. because you can add a seal there. If it's type read-only T, you can add a seal, it'd still be type read-only T. And progress and preservation ensure that the modified term will reduce and not get stuck. And with those handy-dandy equivalence lemmas back here, the equivalence lemmas ensure that the modified program and the original program reduce the same way, while modulo X are seals. So you actually get a guarantee here that in this setup, programs that have references that are typed immutable but aren't sealed aren't written to. And that's kind of cool. So that's my talk. Thank you for your time. And if you have any questions, I'm happy to answer them.
Okay, we have plenty of time for questions. Please come to the aisles if you have a question.
Thank you for your very interesting presentation. I'm Clément Blodeau, PhD candidate. What you said made me think a lot about private types of OCaml. So in OCaml, you can have private types where you said that the actual implementation is something like integers, but you can once you've you can take a private type and look at the value as if it were an integer, but you cannot rebuild the value back in if you've modified it. Does the read-only construct that you have in types correspond in some way to the private type construct?
I'm not that familiar with OCaml, but I'm happy to talk about this after and think about it, because yeah, I unfortunately haven't thought about that question too much in detail, but I'd be happy to talk about it later.
Hi, over here. So can you have mutable references that alias
Yes.
mutable references?
So in reference immutability, yes.
Yeah,
This isn't,
fine.
we don't talk, in this setup, we don't care about linearity or ownership.
Good, right.
Yes.
So instead of asking a question, I'm just going to address the whole room and say, can we please stop calling read-only reference immutability? Because I think it's a lie. I mean, it feels, many times you like drop the word reference from reference immutability, and you talked about transitive immutability of objects, and they aren't really immutable, right?
Right.
If you have a mutable pointer to them, you can change them.
You can,
so we used to call this a read-only reference, but
Right.
I think reference immutability, that's fancy, and it sort of has a nicer property, but it doesn't, right? Because they aren't immutable.
Right,
Yeah.
for sure.
So this is the term that needs to die.
So James has told me the same. James Noble has told me the
Yeah.
same thing. So
Good. Good for James.
I'm happy to look. I'm just using what's in the literature. I'm happy to change.
Yeah. But there's other literature that uses read-only.
Right.
So please, also cite those papers.
For sure.
Thank you.
Okay. Okay, so I had a question. Sorry. Did this language have higher order functions also?
Yes, it's system F sub.
So then how does the read-only interact with the higher order function?
So that's the entire thing with like subtyping and read-only, because you will get types like read-only, 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 read-only T. So like that's in the paper, but you have to actually work a little bit to show that. And it's obvious that like read-only, read-only, read-only is the same as read-only, right? But you actually have to like in the paper in our cock proof, which is available as an artifact accompanying the paper, we actually worked pretty hard to show that types come in a normal form with one outermost read-only, and you can always show that like a term gets typed can be given a normal type, and then that allows us to actually do inversion limits, so we can get progress and preservation.
Okay. And I couldn't help but notice the property that you prove, this equivalence lemma.
Yes.
It seemed very similar to a property that we prove in gradually typed languages.
It's also true. It's also really so. Like this is actually. I was thinking about where I got inspiration for seals, and I did my undergrad at Waterloo, where we talk about racket and racket contracts.
Yeah.
So this is so like you can view like sealing and all these equivalence lemmas as like as a form of like rackets, I guess. Rackets, not imposter. It's a
chaperone?
Chaperone contracts,
Yeah.
that's right. So they're a form of rackets chaperone contracts. And in the paper, we actually show that you can actually model reference immutability in racket with chaperone contracts as a nice little thing in the related work.
Great. Okay. Well, if there's no more questions, let's thank Edward.